Hey everybody, welcome to episode 7 of the MicaSense podcast. This is your host, Drew Bostian. I'm here with Stephen Mangum, my co-host. Stephen, how are you doing today?
Howdy, Drew. I'm doing wonderful. It's a really beautiful time of year here in Seattle. We did some drone flights yesterday out in the field and got to get the sunscreen out and the allergy pills taken, and everything's just really great out here. I'm sure it'll start raining any day now again, but yeah, it's just exciting to be talking to all the researchers and helping everyone out, and also help develop new products here at MicaSense.
Today's episode, we have a special guest, Yu Jiang. Yu, did I pronounce your last name correctly?
Yeah.
Yu Jiang.
Wonderful. Yep. Jiang.
Okay.
Yeah.
Great. So Yu is the assistant research professor at the School of Integrative Plant Science at Cornell AgriTech in Geneva, New York. So it's kind of a branch of Cornell University in Ithaca, but it's based up in Geneva, and I'm sure we'll learn more about it today. But we've done some stalking of Yu prior to this call, and he's got an extensive background in agricultural research and has tons of publications. And given that we have a really solid academic research customer base, I think this will be a good episode on that front. So, Yu, thanks for joining us today. We really appreciate it.
Yeah, thanks for having me here, Drew and Stephen. Glad to share some of my thoughts with all these MicaSense users. I really like the sensor, by the way.
Oh,
that's great. Thanks.
Thank you very much. So maybe we could start by you giving us a background on yourself and how you ended up at Cornell AgriTech.
Yes, Drew. So my name is Yu Jiang. As Drew just mentioned, I'm currently an assistant research professor at Cornell AgriTech. So my research program primarily focuses on systems engineering and data analytics for specialty crops. So basically, we develop different agricultural robots and AI-based analysis tools, try to understand agriculture and to really provide a data-driven solution that can support the new revolution of agriculture, so called digital agriculture. So back to the question, what is AgriTech, right? I think this probably is a very new brand name for most of the outside people. But actually, we have a long history of a legacy in agriculture. So formerly, we are the New York State Agricultural Experiment Station. So we have we can trace back our history back to 1880. Okay. That's more than centuries ago, and we are dedicate our focus to really help local growers within the New York State, within a wide range of different agriculture sectors. From like a car industry to food and vegetable industry, all the way down to some basic science related to specialty crops. Especially we have in collaboration with the USDA-ARS GGRU station here in Geneva, we own two world largest population of apples and grapes. And those also being kind of our history, and we really provide all these prestigious cultivars to the customers within the US and worldwide. And for example, we have a very famous apple cultivar, Snapdragon, probably consumed most of places in the world. Yes, so then I think just in about 2018 or 19, we just rebrand ourselves to Cornell AgriTech, try to reflect the importance of incorporating cutting edge technology for agriculture, both in research and production. So that's the reason why we choose the name Cornell AgriTech, really try to highlight the importance of the technology for the future of agriculture.
You came from before Cornell. You came to Cornell from University of Georgia.
Yeah.
And so you were studying there. Can you give us some information on the work you were doing down at University of Georgia and what led you to Cornell?
Oh, yeah. So that's also related to my training background. So by training, I'm actually an engineer and a computer scientist who are just by chance working with agriculture. So I did my PhD at the University of Georgia with a special focus on agricultural and biological engineering. And there I primarily deal with two crops. One is cotton, which is very important for those cotton belt states. And the other is blueberry, is also kind of I remember now Georgia maybe number 2 producer within the U.S. So it's a kind of an important crop for the state of Georgia there. And my research topic was focusing on development of new technologies or sensing tools that can help the researchers and the growers to get some important traits from for these two crops. For example, I worked with a cotton breeder and a large genetics team to develop new high throughput plant phenotyping systems for cotton breeding and genetics studies. And there we, to measure basically just a simple cotton plant height all the way to, the number of cotton balls on each plant, so that the growers or insurance companies can use those information to do the yield estimation, and eventually, that would relate to the economic value of the cotton per year based on the data we get in hand from the field, rather than just some, historical, value estimation models. And that will give us some more confidence, to see, oh, this year we will have, number 8 yield of the cotton ball with certain grade of the quality, and we can expect the market can consume, how much portion for different purposes. And that, is the purpose how we can really rely on those digital technologies to guide us, not only for the agricultural operations, but also the agricultural economic market. And also same thing for blueberry, we are developing actually phenotyping tools to identify blueberry bruise, and that's very interesting project. I think as a kind of a related ag-related industry, you might know U.S. is facing tremendous challenges in finding the laborers for agriculture, and particularly for harvesting. And that happened exactly for the blueberry industry, in the southern states, Georgia, Florida. Especially with the recent, policies on the, immigrant workers for agriculture, all these growers start to see, great challenge in hiring people for hand harvesting. And then, more consumers actually prefer to have those fresh market berries, being picked with high quality, so they really enjoy the flavor and, all these nutrient values from those fresh market produce. But on the other hand, we just lack of the capability to really harvest them. So I think 1 year I heard a story for one of the research farms in Florida. The growers cannot really afford the hiring cost. They just allow the berries just spoiled in the field, try to really save their profit. Because if they invest more money in labor, they actually gonna reduce their profit, because the labor cost is much more than the profit they can get by selling those berries. So that's the reason, all these growers are seeking for mechanical or robotic harvesting technology. But then back to agricultural question is that, do we really have the cultivars that can provide such capability to develop a mechanical harvester for them? Because if we talk about, this giant machine, either, a shaker or a spinning tool, inevitably we're gonna generate tons of impact on the berry themselves, and then you will have bruise. And once you have some bruised fruit, that's gonna impact your economic value for sure, your flavor, and your transportation. Especially consider if you need to ship the berries from Florida to California, how long that take, and when those berries arrive at the destination, and the market already being closed for those berries because they're degraded quality. So that's a reason, we see this problem from both sides. So from the engineering side, we develop new, harvesting tools like soft robotics, try to mitigate the impact being put on those berries. But on the other side, we help agricultural scientists, breeders, try to find new cultivars so that they can have a better, crop itself that tolerates to a certain level of impact. So if we work from both ways, we probably have better chance to really solve that in an innovative way.
Yeah. So that's something that you don't naturally think about. You think about, how can we make robotics and technology, hardware technology that can harvest blueberries as they are, but I mean, it's not natural. I don't think it's a natural thing to think, hey, we could actually make the blueberries become more mechanically harvestable, So you're basically, like you said, you're meeting in the middle. You're modifying the plants so they can be more easily harvested, and then you're creating technology that can actually harvest them.
Yes,
that's pretty
exactly.
interesting. So you mentioned high throughput phenotyping. I feel like that's a term that gets thrown around a lot, and I think there are people out there who are afraid to admit that they don't know exactly what that means. So I think it'd be good, if you don't mind, if you could just give us a definition of what that means, high throughput phenotyping.
Okay, sure. Well, first, I'm not sure if I'm really qualified to formally define that, because this is a kind of a long-term being defined by those agricultural scientists. But my understanding is that so we have the phenotyping facility or work always done to Mondale, who observed all those peas, right? That's called phenotyping. But now we just have a substantial needs to phenotyping more and more crops. Just as I explained, for example, if we want to choose a right cultivar, blueberry cultivar tolerated to impact, we need to screen out thousand or hundreds of thousand plants, and just try to find maybe one or two cultivars being suitable for our purpose. Then that's the reason why we come out with the adjective high throughput. We really need to deal with a large portion of candidates and then narrow down them to just one or two cultivars being finally released on the market that for us to use. So typically this breeding cycle takes about 10 to 20 years in the past. And now the number one question is that by 2050, the global population will be projected to exceed 10 billion. And then the number one question I always ask my students is how you as a single person get all your food and daily supplies from our agriculture industry. That's a tremendous challenge for everybody to think about. Especially we do not only to deal with the growing population, we need to consider all this climate change recently we all experience. We have shortage of water, we have extreme temperature every day, especially during the growing season, right? I think last year we just did not receive such more water in New York State, and that's caused some irrigation problem we never faced. Or just in the southern part in Georgia, they face the irrigation problem every day because they already, have the heat, strong heat every day from the sunlight. So that's the reason we have to shorten or speed up the breeding programs so that we can really quickly find all these cultivars we need that fulfill our needs. And by the way, also another new thought in my mind is that now NASA already launched the robot, landed on Mars. But in my opinion, if we as human want to land on Mars for whatever reason, the first challenge is also the food supply.
Sure.
It's impossible for us to always transport the food from the Earth to the Mars and supply people there for long term. So we have to find a way that we can grow something, either in our spaceship or just on Mars directly, so that we can supply people there. And still, that going back to the fundamental question, how breeders can find those cultivars for us to fulfill all these future, projections? And that's a really critical question. And that's why we start to, develop those high throughput phenotyping tools, try to solve these, challenges from the academic side. But at the same time, I think precision agriculture is a kind of acronym or term being used a lot. But a lot of the fundamental needs for precision agriculture is also for phenotyping. For example, if you want to precisely control your irrigation rate, you have to understand how much water your crops really need at that time. And they vary a lot, even within the field. Particularly, for example, in the vineyard, microclimate gonna dramatically change the grape quality at the harvest time. Then how you do the variable rate, irrigation or spray to really make sure you have a constant quality throughout your vineyard is also kind of a challenge for everyone. So that's all coming out back to the question, how are we gonna measure and screen our plants in the field? And that's a reason why we do this high throughput plant phenotyping, try to address these fundamental needs.
So it's another way you could say it is it's like accelerated phenotyping. You're doing something that used to take 10 to 20 years, and now maybe it's taking 2 to 3 years, or would that be an accurate way of?
Yeah, maybe not really 2 to 3 years, but definitely we're gonna just shorten at least 10 to 20%, in my opinion.
Okay.
And how do the drones or the multispectral or hyperspectral imaging come into that phenotyping, or is it mainly still manual for each of the cultivars?
Yeah, that's a great question, and that also let me just recall my PhD life there. So initially my PhD not really on the phenotyping project because I joined University of Georgia in 2013, and back then high throughput phenotyping is not really even hot within the engineering side. So the trend actually aligned with the start of MicaSense. If I remember correctly, my old lab and I was the first batch of user of MicaSense.
No way, that's awesome.
Truly, yes. So that's the reason, when I first time heard the high throughput phenotyping project, I'm excited what I could do to help agriculture. And then the first sensor research is multispectral camera. And back to that time, I think end of 2013, the only one available on the market is it's called MCA camera, if I remember correctly. And it itself costs $20,000 or $30,000, but it's just a 6-band camera. And also it's pretty heavy. And if you want to mount on a DJI drone back that time, that means you have to do substantial modification on, securely putting and holding the camera while you fly. And everything is just being too challenging for even researchers and experienced engineers to develop and use. So that's a reason I think in 2014 we see the first red edge camera from MicaSense. I will say, okay, that's exactly the sensor we like to use. Because by using a portable and lightweight camera, we can easily integrate with commercially available multi-copter drones, and then we can immediately fly and get the data. And the first thing from the multispectral camera we get is the NDVI value. I think we talk about NDVI a lot within both agriculture and engineering field, and because they have tons of meaning to help you quickly manage your field. Like even though the index itself has a lot of disadvantages and limitations, but still that's a kind of a quantitative metric you can rely on to see what's the change, what's the spatial variation in your field, how your plants change over time, and how you can dig more information, as I mentioned in the breeding program, how you can quantitatively analyze them to find more interesting findings from the genetic side and help to breed the cultivars. And for example, if we did an experiment with the heat tolerance, and the heat tolerated cultivar will show substantial different, NDVI values than those ones not tolerated to heat stress. And that's exactly, what we expect to see. We can rely on some, index or quantitative metrics to show the difference and then do more analysis from the biological side.
But that's crazy that you got one of the first cameras. Do you know who was the professor who ordered the camera, or did you place the order?
I think either my colleague Dr. Ray Xu or my former PhD advisor Dr. Changyin Li placed that order.
Okay, interesting. I'll have to dig around for that.
But actually, I and my former lab was a kind of a first batch of MicaSense user.
Okay, it probably was a Red Edge 2. Yeah, the feedback was that it was a lot better than what else was available on the market at that time. So that's pretty cool.
Oh yeah, that's much better. Especially with I think following up, upgrade with the sunlight sensor that can do the calibration for the images. That just solve tons of problems that later on for data analysis. Yeah.
So with the cotton yield stuff, was it exclusively the Red Edge that you were using for that kind of work, or were you using? I saw in some of your publications you mentioned Hyperspectral and LiDAR. So can you tell us about maybe your uses for multispectral versus hyperspectral versus LiDAR for the blueberries or the cotton yield, if that's applicable?
Yeah. I think actually we use the multispectral LiDAR and hyperspectral for both crops quite intensively, but for different purpose. So one of the key projects in that kind of large, team efforts is to quantify or characterize the cotton flowering time. So as I just mentioned, when you treat your crops for management, right, you need to understand them better. So Georgia versus, for example, the other large cotton producer, Texas, they have totally different climate. And then, the cotton will grow in totally different patterns. So in Texas, the cotton tends to, just grow quickly and until a point that you can quickly, form the flowers and then eventually convert them to cotton balls. But in Georgia, we just have a much longer time that allow the plants to gradually develop everything because of the climate difference. And then, it's very important for us to understand or measure what's the flowering time for different cultivars, and then we can select those, for different places that maximize the yield. And particularly for flowering detection, we use the multispectral camera, and we use the deep learning model so that we can identify the flower from the multispectral images. Well, actually, part of the reason the detection accuracy is pretty high is because the flower has distinctive features than the plants in 2 or 3 bands that only multispectral can provide, as compared with RGB. So actually, those would provide significant help or information that help us to develop a simple and reliable algorithms to find them. And I think that's actually a big difference. So as I mentioned, I'm not only a computer scientist, I'm also an engineer. And from an engineer perspective, the number one question is that whether or not we can find the difference by using different hardware, right? So if we can produce a hardware that can naturally show the difference, that's great. Then everyone can see the difference. And we can design much simpler ways to process the data and get much reliable outcome from those images. Otherwise, for example, if I shoot a color image and tell you, okay, select the white hair from the cotton fiber, I even don't know how people can do that by just seeing the picture, right? Basically, they just some very thin and white reflective object. And I don't really believe any computational method really can do that in a very reliable, and accurate way. So I think that's the difference. By looking at their difference or spectral signature, we will be able to generate the feature and use a much reliable computational method to do the differentiation. And
Okay.
that's actually helped us a lot. So then actually that's naturally to the hyperspectral part, because that's actually why I see sometimes researchers want to use hyperspectral, is because we just simply don't know which spectral band gonna be more efficient than the others, right? If you tell me, okay, the cotton ball will show certain signature at certain band, then I probably will customize the multispectral camera so I expect to see the significant difference at that band. But before we having that capability, we need to explore which are the spectral bands or spectral range suitable for different tasks in hand. So that's actually why we choose hyperspectral. So specifically in the blueberry bruising project, we first used the hyperspectral imaging system, ranging from 900 to 1700 nanometer. And then we found several bands like at 900, 1200, and 1400 show substantial differences between the healthy and bruised tissue of blueberry. So if you use your naked eye, blueberry, they are just kind of dark in appearance. You see no difference if I place side by side for healthy and bruised bands. But if you pick those particular bands, you will see substantial difference. So bruised always absorb more light and then showing darker than those healthy tissue. And then with that, I think at least this is still ongoing. We are trying to find a way to develop a customized multispectral camera. Then we can significantly reduce the data redundancy, right, from the hyperspectral one, and also reduce the cost. Then that can be eventually used for practical scenarios. For example, in the packing line or even on the harvesters, we can quickly sort out those bruised berries and really enhance the quality. So that's the difference here. And as compared with LiDAR, I think that's a kind of a totally different type of sensor that can provide unique information. I would say instead of compare them, why not just merge them or fuse them, right? If we can use LiDAR, get the 3D information from the field and overlay with the multispectral or hyperspectral information, then we can get even more information about both the plant structure versus their nutritional status, for example. And that gives us more information for breeders to select. Because also breeding is not a very simple task. You need to consider not only the one give you the best yield, but you also need to consider whether or not the yield is from a kind of efficient way of using the sunlight, for example, a better photosynthetic rate, right? And that's related to the plant structure. Some will just be very bulky to receive almost all the sunlight from the ambient, but then you will have the problem because you cannot grow them too dense. But some of them, maybe they have some subtle leaf structure changes, and they will produce pretty small canopy, but can use the sunlight more efficient. And then they probably will have a little bit lower yield if you compare individuals, but in general, you can plant them more denser and get a much higher yield at the field level. And so all this information, I think, cannot be provided from a sole source, sensor. We must consider how to combine different type of sensor and use the information together.
Yeah, that's interesting. So you could create a plant that just produces a massive amount of yield, but maybe it covers 4 square feet of ground, and you can only plant maybe 100 of them per acre or something like that.
Yes, correct, exactly. a giant cotton tree.
Right, exactly. You could have 4 giant cotton trees or 4,000 little cotton plants, and
yes.
Yeah, that's interesting. Yeah, hadn't really considered that. So you mentioned 900 to 1700 nanometers for the hyperspectral. is that the only hyperspectral you used, or did you use hyperspectral with a range that went into near infrared and visible as well?
Yeah, so actually I'm being very fortunate during my PhD. I had the chance to work with all these different type of hyperspectral sensors, ranging from 400 always up to 2500 nanometers. So a kind of a full spectral range.
Okay.
Yeah, and we use the linear visible near infrared really for plant canopy study. Because most of the canopy information or their phenology changes can be reflected from this range. And of course, compared with other spectral ranges, this range will also require just a lower cost sensors and detectors. And that's being relatively more practical for most of the labs to do the research. So one of the study we conducted is back to solar-induced fluorescence. I'm not sure if you being familiar with this term, but basically is we use the sunlight as the excitation source, and the sunlight excites the the chlorophyll inside the canopy, and then the canopy will emit certain fluorescent value in the kind of red range. And because of the sunlight has certain natural absorption, right, at certain band, and then we will need to find those bands to retrieve the fluorescent signals from the canopy reflectance images. So that's the reason why we call it a solar-induced fluorescence. And with that, we don't need to worry about whether or not, we need to fully cover the canopy, right, to provide artificial illumination. Then we can rely on just the natural sunlight and find the difference. And those solar-induced fluorescence gonna be more sensitive to reflect the plant status. For example, if your plant experience any stress in the past 24 hours, it can immediately show the difference. And I think some studies even show just after applying some herbicide to the crops, it can show the difference within 2 hours. So that means this is a very sensitive probe that can help researchers to understand the plant's response to different stress. And back to that question, I think Drew, you mentioned reduce the breeding cycle from 8 to 10 years down to 2 to 3 years.
Mm-hmm.
Maybe that's one viable option we can explore, because you see, usually you need allow the plants to develop for days, right, to see the difference between healthy versus those stressed ones. But now if we have a more sensitive probe that can reveal the difference just within several hours, right, that's actually been the time we see.
Okay.
And then, by see the difference, we also see the time for all the processing procedures. Like the researchers need to prepare the plant material, right? They need to put them into the field, really grow them, and allow them to sprout and grow a little bit, right? At least to the seedling stage for the next cycle of breeding. So we just save all the time, not only the measurement, but all the following time during the breeding cycle.
Okay. So when you were looking at the visible and near infrared hyperspectral data, were there a number of cases where you were seeing spectral bands that were advantageous for your work, that were outside sort of the typical blue, green, red edge, and near infrared that say you could find on the red edge, like 475, 560, 668, 717, 840. Were there a lot of cases where it would be more beneficial to have a custom camera? I guess I'm just curious to know on that front, or were those 5 spectral bands generally, are those going to cover pretty much all or most of the applications?
Yeah, I think for most applications, those 5 bands would cover, the indices being effective and useful for the applications, either in breeding or management. But if as a customer, I actually would ask, if the company would start to think about, because one important thing compare multispectral versus hyperspectral is the spectral resolution, right? for hyperspectral, we probably can achieve like up to 0.1 or 0.2 nanometer for the spectral full width half maximum, right? But back to multispectral, usually we see the number like at least 10 nanometer because of the limitation from the optics. But sometimes I do see, for example, if we want to do the solar-induced fluorescence, we have to rely on high spectral resolution to reveal the difference. Because once you get too many, coverage at a certain band, then the subtle difference at that laser band will be averaged by the surrounding information. Then
Sure.
we lose the capability to really reveal the difference between crops.
Yeah, that's interesting. And I think a lot of times we come up against the question of why are narrow spectral bands important? And I think we do a half decent job of addressing that as a sales and from a sales and marketing perspective. But it's interesting to hear from you that that's really critical to get kind of the narrow spectral bands and specific, being able to narrow down and focus on a specific center wavelength and bandwidth and not getting noise from the surrounding area. It's important.
And what kind of resolution are you getting with the hyperspectral, like the image resolution?
The spatial or the spectral?
The spatial.
So the spatial we use is, if I remember correctly, it's around 2,000 pixels along the.
Oh, wow, that's a lot better than I'd expect.
Yeah.
So what would that be in GSD, or like you're flying that on a drone, I'm assuming?
So we actually mount on a customized robot that's up to like 1.5 meter above the plant. So if you convert to GSD, I think that's gonna be like a millimeter resolution.
Yeah, sure.
True, yeah. That's your dream of having a pole mount robot.
Yes, exactly. So we actually prefer to get this detailed information, but also totally depends on the specific application. So if you are dealing with, for example, 100 acres or 1,000 acres of the plants, and to reveal the difference, then you even won't be able to scan the field within valid period of time with that resolution. So you have to rely on drone or other aircraft to cover this large field. But if we are dealing with very fine-tuned experiment that not having very large acreage and prefer to get as much detail as we can, then we prefer to just use kind of a proximal sensing to get all this information we have.
So when you were using the red edge, or when you have, at Georgia and at Cornell,
yeah,
are you flying super low like that? I mean, are you trying to get within 10 meters, 20 meters of the canopy, or are you flying more of a traditional height of like maybe 60 to?
Yeah, we actually did all this. We haven't published some result, but we did experiments, try to compare different flighting height, how that affect our final measurements. I think some quick summary or taking home message is that for some time sensitive sensors, for example thermal, would be better to just fly as tall as we can while maintaining the spatial resolution we need. But otherwise, we prefer to fly as close as we can to get the details so that we can rely on not only the spectral difference, but also spatial difference to build up a more robust algorithm for different purposes. As I mentioned, for the flower detection, so that's very interesting because each cotton flower is about like 2 to 3 centimeter in diameter, right? And if you fly, like say 50 meters above the ground, then each flower becomes to just 2 to 3 pixels in the final multispectral image. And while we still can rely on spectral difference to see this is potential a flower, but we still need to add more assumptions in our algorithm to make sure the detection accuracy Versus if we fly just 15 meters above the canopy, then each flower really sees a flower in the final image. That's just help us a lot to build, for example, the convolutional neural networks to identify the flower based on both spectral and spatial resolution.
Okay.
Yeah.
So what do you think you and your colleagues and really like the whole agricultural research community is seeking in terms of spatial resolution? Is it just like millimeter level or sub-centimeter or a few centimeters? Like generally speaking, what do you think the target is?
I would say generally, everybody would have the resolution as higher as possible. See, if you can provide millimeter, that's great. Okay. Even micrometer, that's even greater. But also, I think an important thing for researchers is that if vendors or companies are willing to provide the flexibility in customizing the camera for their particular application, that would be important. Because for example, if off the shelf products we only has a certain resolution, then the only way I can control the resolution is to just fly lower, right? And just enhance the spatial resolution. But if the vendor or company willing to work with the academic researchers together to customize the detector, say improve from 8 megapixel to like 20 megapixel, I think that's gonna be much easier for everything, and also provide a lot of flexibilities for different usages. Like still, I'm currently working with Larry Smart for the hemp industry and also hemp breeding programs. I think he mentioned one thing is about the flowering of hemp. And if you see the hemp flower, they are pretty tiny, even smaller than cotton ones. The critical challenge we are facing right now is how to use the current resolution to really pick up all these flowers, right? If a UAV gun not be the option, we have to rely on the robot to do the proximal sensing, and even need to put the camera closer. But also, of course, we have some focal distance limitation there. The camera cannot be placed too close to the object or plants. So that's a reason, if there is a way that academia can work with the industry to develop customized sensors for different crops, not even just for individual crops, but for different types of crops. For example, we have tree crops like apple, peaches. They might not really require that high resolution, but for vegetables or hemp, they have a structure that require high resolution. But if we have such flexibility there, I think that's going to be wonderful.
Okay. So are you using the Red Edge or the Altum or any of our cameras at really, really close proximity, like within a few meters?
Yeah. So before I left Georgia, actually, my former lab has a project to place the multispectral camera only like a meter away from the object to reconstruct the 3D structure of blueberries, and while overlay the multispectral layer on the 3D model.
Okay.
And that's the closest distance I have been working or involving in.
Yeah, that's definitely a pain point we see, is people wanting to use it really close up. One theory I've heard people talk about is having like a robotic arm that would move the camera slightly so that every band is eventually taken from the exact same point in space, so that you would eliminate that parallax effect. Is that something you've looked at?
Yes, definitely. And of course, we are trying to incorporate the 3D information because as engineers, you all know that the morphological structure will affect your reflectance angle, right? And then your measurement needs to be correct, especially when you place the camera very close to your object. All the subtle geometric changes will affect your final spectral intensity. Sure. And we don't want those artifacts being involved in the final data. So using robotic arm plus using some 3D information there, I think that would be a way how we can crack the spectral reflectance.
Does this robot have the DLS attached, and are you taking panel captures as well?
Yeah, so we have several different setup there. But currently in my lab, I use kind of photogrammetric method, which we use multi-view stereo. So we attach like multiple cameras from different angles, try to reconstruct the 3D structure, and place the multispectral in a fixed position. And then later on, we overlay the multispectral layer on top of the 3D layer.
Okay. I've seen that in use before too.
Yep. And of course, we can use other stereo camera or TOF camera, time of flight camera, for that purpose.
So you mentioned NDVI earlier, and then I think also when you were talking about the flowering, you said that there's like 2 or 3 specific bands that were useful for identifying the flowers of the cotton, and that just made me think, like, can you talk about any indices or composites that are outside just the typical NDVI or NDRE? I think our listeners would be interested to hear just like about a couple of those that might be like outliers that people maybe don't typically use.
Yeah. So I think if you check back those vegetative indices, there are a bunch of things you can calculate. And I think you can get those equations from USGS, their website. I cannot remember exactly every equation there, but you can check the list. But there are some modified indices that can be used for different purposes. For example, if you are looking more for soil quality, there are a bunch of indices there for that purpose. And if you are more interested in the water status, there are also some indices designed for that. But still, I think a more important thing from the research perspective is the possibility of different combinations from those bands. That's still being a kind of research topic. By just tuning those bands, in different combination ways, sometimes I do see significant improvements as compared with NDVI.
Okay, so composites instead of indices, you're seeing advantages. That's cool to hear. I feel like we've done a lot of classification toying around with, and Stephen could probably speak to this better than I can, but I think our sales engineer, Callum, has said that, well, maybe not. Maybe he's using NDVI or indices quite a bit, but it seems like composites can be really useful when it comes to classification.
Yes, correct.
What was it that drew you to Cornell? Was that, you're going from a cotton area in Georgia to really diverse research opportunities at Cornell AgriTech. I guess what was the initial draw to making that move?
Yeah, so I think also that's related to my PhD training. I believe I'm probably also the first batch of PhD students being trained really in an interdisciplinary team. As I mentioned, as an engineer, I received very rigorous training for all these engineering, principles, theories, and develop new engineering systems. But at the same time, I also received considerable mentorship from like breeders, geneticists, plant physiologists, and all this information coming to my head and making me, think that the problem from all different aspects to come up with new solutions. I think that, well matched with what Cornell and Cornell leadership's vision in this area. So Cornell is currently initially has the initiative called Cornell Initiative of Digital Agriculture, CIDA. And now the initiative already turns into an institute, Cornell Institute of Digital Agriculture. And the whole university, from the president to all these, department chairs, and would really, value the importance of having, technology for agriculture in the next, 10 to 20 years. And that's gonna help us to reshape agriculture. So maybe after 20 years, we no longer see the agriculture industry like the day that they look, as today. And especially by having all these, robotics and AI technologies, we're gonna significantly change the industry. And of course, I think one of the important impact is from the social part. Many people would be worried about or concerned about the job, opportunity, right? By having all this robotics, how people will find a job in the industry, especially in agriculture industry. But in my opinion, with the new revolution of digital agriculture, we're gonna create more jobs in agriculture, and we're gonna attract more young generations going back in the agriculture industry compared with the situation right now. So think about that. So previously, you just hand-pick blueberry, but now you need to work with robots, and you do not only work with them. You need to have basic knowledge in engineering or in computer science, how to operate them, how to interact with them, how to maintain them, and all of these just help us to enhance our educational, opportunities for the young generations. Everyone will receive, great support in those domains, and eventually work as a high-tech industry. Many people complain agriculture is not that, still like a dirty work area. But I believe with all this technology advancement, we will eventually create a high-tech agriculture industry. So everybody will be interested in and attracted by it.
Yeah, I agree with that. It seems like the more people propose new technologies in agriculture, the more money gets invested into it, and the more people have opportunities to work in the space. At least that's what I've seen, just in terms of like ag tech companies and the venture capital that's been put towards that. I feel like there are many more jobs in agriculture now with the advancements we've seen in technology than there were 15 or 20 years ago. So
yeah, exactly. I also want to just add some addition there. So even NASA forms a particular initiative called Harvest, and that can work with academia researchers who are working for agriculture. So basically, NASA is putting efforts and they invest significant resources for agriculture. I think that's also somehow reflect the importance how we use different technologies for agriculture and from different levels.
Yeah, absolutely. Speaking of NASA, I mean, you mentioned growing crops on Mars or in outer space. Maybe as like a final topic here, since we're running out of time, what's your vision for how that could look? I think I'm
so
always interested in that kind of topic.
I really the person like to see the future, even just imagine the future. But first maybe let me introduce some reality. So I have several partnership labs led by Dr. Kitty Gauld at Cornell AgriTech as well. So we are working with closely and we are trying to building the relationship with NASA so that we eventually can use all the satellite imagery from NASA, help the grape industry within New York State and even beyond. And one important layer we are working on is to create a multi-scale sensing system. And I think the system with the current dual red edge would be critical in that kind of connection. So we hope to learn some high resolution information from the local drone or proximal sensing system with different sensors like the multispectral, and eventually can find the knowledge being applied back to the satellite imagery.
Interesting.
And that will help us to substantially enhance the sensor availability for growers. Because still, I know, MicaSense is great to make effort in, making the multispectral camera much more affordable as compared with just a 2014 or before, right? As just explained. But still, that's gonna be a considerable cost for most of these small to medium-sized farmers, and they are struggle. But they still want to use digital technology to help them to enhance the quality, to improve the productivity. And we see the way NASA can help here is really to use the satellite imagery that can help all the growers across the nation. And then more future things, in my opinion, is that like NASA also start to open more and more challenges, competitions, and concept proposals to see how we can really bring agriculture with the space, right? With the universe. And I really imagine, one of the things we want is to grow grapes in the spaceship so that our astronauts can also have their grape wines maybe made on the spaceship and enjoy some time while flying from the Earth to the Mars. Sometimes
maybe that would be a really lucrative business. I mean, can you imagine how expensive a bottle of wine would be from grapes that were grown in space? And there's probably like wine connoisseurs with enough money to actually buy a bottle of that. So
maybe, and if we can imagine we have a bottle from Mars back to Earth,
yeah,
that's even more interesting.
Cool. Well, Stephen, do you have any other questions?
Well, on the topic of wine, there is a question here about the Craft Beverage Institute. Is that something you can tell us about?
Yes. So we have certain conversations with the Craft Beverage Institute, especially about the wine industry, and I also work with several viticulturists and enology, researchers, try to understand, how all these technologies being deployed in the field will eventually help the improvement of wine quality, or at least, make a consistent quality of the wines from the grapes being produced from the Finger Lake area. But I think more and more people now start to enjoy the bottles from Finger Lakes.
Yeah, I've actually I've been to a number of those vineyards. So I went to Cornell for undergrad, so I'm pretty familiar with the area.
Wow.
And I think was it Sheldrake? Sheldrake is my favorite. I don't know if you've been to that one.
I think Kitty mentioned once to me about that place. So Kitty and I prefer actually Anthony Road, just down the road, Geneva. It's closer.
Okay.
Lake Seneca.
Oh, Seneca Lake. Okay.
Yeah, Seneca. Yeah, but I think Drew and Steven also, you have time, you probably need to stop by and really try to visit all this vineyard.
Yeah, we really should. There's if we needed to take a trip to just collect a ton of data sets, it seems like upstate New York would be a good place to go.
Definitely. Oh, for sure.
Yeah. So, Stephen, we'll have to pencil that in for maybe Q3.
Yeah, I agree. Once we we're able to get out more, and yeah, sounds great. We should do it.
All right. Well, I think we should probably wrap up. It's been really fun conversation. I really appreciate your time and just sharing a little bit about the research you're doing in remote sensing and multispectral imaging. And I think everyone's going to really value the information that you had to share. So thanks for coming on. We appreciate it.
Yeah, thanks to Drew and Stephen for having me. And it's my pleasure to share some of my thoughts with all these audience who will use the multispectral or maybe other sensing technologies for agriculture.
Yeah, thanks so much.